Hello there. In this video, we are going to go through the second tutorial. So the previous videos were installation and going through the first tutorial. Now we're going to get to something that I think speaks to some of the generality of the queuing models that the queue package can supply. So if you remember in tutorial 1, we had this idea of creating a network, but we only had one node for each of these inputs. And what we're going to do in this video is generalize to multiple nodes. And we're just going to follow along in an example from the documentation. I should put back in there, but what do I want? We'll go tutorial 2. And for the moment, we'll go through the tutorial in the documentation. So queues' real power comes when modeling networks of queues. That is, many service nodes, such as when customers finish service, there is a probability of joining another node, or rejoining the current node, or leaving the system altogether. Imagine a cafe that sells both hot and cold food. Customers arrive and can take a few different routes. Customers only wanting cold food must queue at the cold food counter, then take their food to the till to pay. That makes sense. There's like a natural constraint there that you don't pay at the till before you get your food. Customers only wanting hot food must queue at the hot food counter and then take their food to the till to pay. Same idea. Customers wanting both cold and hot food must first queue for cold food and then hot food, and then take both to the till to pay. Now, that's kind of interesting because I think often people wouldn't really care if they, strictly speaking, got cold food or hot food first. And maybe in a future video, we'll rewrite some components of the simulation such that the customers may randomly go to maybe the cold one first and then the hot one, or the hot one first and then the cold one, while visiting only each node once. But for our purposes here, we don't need to get into that. We're going to assume that they go to the cold food counter first and then the hot food counter second if they want both. Now, in this system, there are 3 nodes: cold food counter, node 1, hot food counter, node 2, and the till, which is considered node 3 in the simulation. Customers wanting hot food only arrive at a rate of 12 per hour. Now, I think we're going to probably take up in this simulation that the base unit of time is going to be hours, but we'll see. Customers wanting cold food arrive at a rate of 18 per hour, and 30% of customers who buy cold food also want to buy hot food. So in the simulation, we're not going to pre-label all of the customers for which set of preferences they have. Some fraction of them that have gotten their cold food are going to go over and also get hot food. And that percentage is 30%. And that will be decided for each customer when they're finished getting their cold food. So, on average, it takes 1 minute to be served cold food and 2.5 minutes to be served hot food, and 2 minutes to pay. There is 1 server at the cold food counter, 2 servers at the hot food counter, and 2 servers at the till. So this is just like a completely worded version of what we're going to put into the programming tool. Now, this diagram is pretty hard to read because of my affinity for dark mode. So what we're going to do to take a look at the model is I'm going to move it, open up in a new tab. Just fair warning, it's going to be bright white background. So for those of you who don't like getting blinded, this is your fair warning. 3, 2, 1. Everyone still be able to see with their eyeballs. Okay, so this is a visual of the model, which I find so much more helpful. Not that the description that we just got wasn't sufficient, but I just like to see the model when possible as a network diagram. Now, I want to explain the kind of structure of this diagram. Each of the nodes is something that kind of looks like a collection of circles and a thing that almost looks like a ladder. That ladder-looking structure is the queue. That's where the customers are lining up at each till. And the circles are where they're actually getting some kind of service, of where there's an event that is happening that involves the customer, which for the cold food node is getting their cold food there. And then as we were reading, 30% of them branch off to go check out the hot food, where they may have to wait, maybe not. And then there are 2 servers that are going to provide service for handing out the hot food. And then regardless of whether you got cold food first or not, and regardless of the path you took, you eventually end up at the till, where you may or may not have to wait. And then there are 2 servers that are going to help you check out. And then for inputs into the whole system, there's really only two. You can have arrivals from outside the system at the cold food node and arrivals from outside the system at the hot food node. And then there's only one output. The only place where anybody leaves the system is out from the till. Okay, so hopefully that visual is helpful. Next thing that they talk about here is the idea of a network requiring some way of describing the flow, what I often call the routing, and they call a routing matrix. And they describe it as an n by n matrix, where n is the number of nodes in the network, which is fine, such that the ith jth element corresponds to the probability of transitioning to node j after service node I. Now, it's not evident, and maybe I should double check that it's still the case, but where these routing matrices are not 100% the same thing as what are conventionally known as stochastic matrices, where the rows, singly stochastic matrices, where the rows add up to 1. They happen to do that in this example, but if I remember this right, routing matrices in Q do not. So what I mean is, here in this first row, this is the first node, which is the cold. 30% or 0.3 go over to the second node, which is the hot till and the hot counter. The hot, is it counter? What do they call it? The service to hand out? Yeah, counter, hot food counter. And then 0.7 of those starting at the cold counter, when they leave the cold counter, will go over to the till. However, Q allows it so that maybe these are actually both 0.3 instead of 0.3 and 0.7. What would that mean? That Q makes the assumption that any extra probability that's not accounted for in a row, where let's say they were both 0.3, that adds up to 0.6, there's a missing 0.4 probability, hypothetically. That 0.4 would be a 40% chance of just leaving the system entirely from that node. There's also the diagonal, and the diagonal of this matrix means the probability of returning back to the same node that you just left from, or that the customer just left from. And in this simulation, it's 0. So somebody who just got their food at the cold food counter, is not going to immediately go back to the cold food counter. And is that entirely realistic? It's moderately realistic in my opinion, but maybe somebody just got through the cold counter and then they're like, oh, actually I forgot something. So you could actually have some people returning back. That's fine. But we're just trying to explore this simulation, and I'm just trying to point out some of the complications that are just adjacent to this that you could add into the system if you wanted to. Okay, so what is it saying after this matrix here? That is 30% of the cold food customers then go to hot food, while the remaining 70% go to the till, and 100% of the cold food customers go to the till. This is included when creating a network with the keyword routing. So our network for the cafe will look like this. Great, we'll type that out. And I'll try to talk through each piece. Again, there's an interesting component. So, okay, first of all, we are going to import Q. And we're going to give this the name network, just because I'm not a huge fan of just calling it capital N. There's some Python variable naming conventions that would say don't do that, but that's fine. Okay, so we're going to create a network, and the first bucket here is our arrival distributions. Now remember, its first node is cold food counter, second node is hot food counter, third node is the till. So when we're talking about arrivals, we should expect that there's only arrivals at the cold and hot food counters, not at the till. So we'll get to that part at the end of this list. The very first element of this list is the first counter. And the thing I'm noticing here, and they did this in the last assumption, is that we're dealing with exponential distributions again, that the setup of these word problems assumes, and I don't think it's entirely unreasonable to assume this, and I want to explain now why that's the case, is if somebody doesn't give you additional information past a point of saying, well, here are like some of the rates or something like that. One of the nice things about the exponential distribution is that it is a maximum entropy distribution. So out of all the probability distributions that are defined over the non-negative real numbers, it is the exponential distribution that has the maximum differential entropy that's possible. What does that mean? It the gist of it means that you're choosing a distribution that's very flattened out, has a very long tail, and that it's not really going to look like a really sharp peak. A really thin normal distribution, for example, would be a very different thing than an exponential. And if you wish, I recommend you check out, say, the Wikipedia page and you look at some of the distribution plots to see what the shape of it is. Actually, while we're here, why don't we just do that? Exponential distribution. Glad it's not going to embarrass me on Edge. Sometimes it'll be like, you visit this page often. And I'm like, oh, I know. I know. Exponential distribution. There we go. So here's some density plots, right? So one of the things about the exponential is that the most likely thing is 0, which may not be an assumption you actually always agree with. And that's where sometimes there is more information than what an exponential would suggest or give a different probabilities in your mind. But still, an exponential is pretty good as like a default assumption. It allows for a lot of variability, and that if you're just trying to say, well, we need to base our analysis on something, you can use exponential as a default where all you've been given is a rate and you're filling in anything you don't know with this idea of maximum entropy, maximum spreading out. Okay, and that's enough about the exponential for now. We're making the same assumption here for the service, for the arrivals at the hot counter. So exponential rate is equal to 0.2. Remember, as I mentioned in a previous video, that the average of an exponential distribution is actually 1 over the rate. So if we've got 0.2, that this is equivalent to having an average of 5. And then this last one is none. And the last one in this list, the third node, corresponds to the till. There should be no arrivals from outside. This is not the distribution for the rate of arrivals from nodes 1 and 2 into node 3. This is the rate of arrivals from outside the system altogether into the system. Service distributions. Okay, so this is about how fast the service gets completed. So notwithstanding waiting, this is the amount of time it takes them to actually have the server provide the food or for them to pay. Okay, so exponential, here we are. And the rate of this one is 1.0. Good. I'm a little tempted to wrap some of this on one line, or multiple lines for you. Exponential dists, exponential, rate of 0.4, q dot dists dot exponential. And we'll get into a later video on like what if you want distributions other than the exponential distribution. Yes, there are more distributions available in Q, but also that it has an API that allows you to define your own new probability distributions, and we'll eventually get into that as well. So we need to write out that big routing matrix. Q nowadays has some different mechanisms for specifying your routing behavior beyond just matrices, but we're going to stick with their matrix representation for just for the sake of following the example. So that's 100% probability that if you're at node 2, that is, you're at the hot node, that you're going to go to the till. And then this last row is that if you're at the till, you got only zeros, right? So remember I was talking about that the complement probability in each row, the missing probability for the total probability of each row is the probability of leaving the system altogether. So if it's all zeros here, that means that there is a 100% probability, or a probability of 1 of leaving the system altogether once you're at the till, once you've left the till. And the last thing there, remember in that diagram we looked at there were those circles representing the number of servers. Yeah, spelling today's off. Servers, number of servers. So at the cold food counter, there's 1. At the hot food counter, there's 2. And then also the till has 2 servers to help you pay and leave. All right, what does the tutorial say? So note that the arrivals, actually we should probably just double check that this runs. And I think it probably won't, because I think I probably forgot to activate a virtual environment. Okay, so there's nothing wrong in our definition. It's good to double check, not because, you know, you may still have misspecified what your model is, and that running the file will not help you detect that. But if you have some like syntax error where you've misplaced a comma or put a period somewhere where it shouldn't be, or other kinds of issues, just quickly running it can help you with establishing that it's at least not invalid syntax. Okay, so notice the arrival distributions. 18 cold food arrivals per hour is equivalent to 0.3 per minute. So here they're really explaining this property of the exponential distribution. 12 hot food arrivals per hour is equivalent to 2.2 per minute, and we want no new arrivals to occur at the till. Now another thing that, oh no, never mind. Okay, so notice the service distributions. An average, oh, that's the thing, averages, right. So the other thing that you should notice of how we're interpreting the example as it was given is that we're equivocating outcomes with averages. That if we say, well, there's an average of 18, that we put in the rate of 0.3, as if that's equivalent to, yeah, there's some formulas. Actually, there's some theory. Maybe we should leave it for another video. But I just wanted to say the first thing there is that the averages and the outcomes are not the same, and that we're interpreting the problem as given as being as if we're being given the average. That is a heuristic for assigning distributions from background knowledge. It's not the only one, but it is a good starting point, I think. Okay, so let's get back to that paragraph. So notice the service distributions. An average cold food service time of 1 minute is equivalent to a rate of 1/1, which equals 1. Service per minute. An average hot food service time of 2.5 minutes is equivalent to 1/2.5 equals to 0.4 services per minute, and an average till time of 2 minutes is equivalent to 2.5 services per minute. Okay, so they're just explaining how they're converting between rates and averages. Let's simulate this for one shift of lunchtime of 3 hours, 180 minutes. At the beginning of lunch, the cafe opens and thus begins in an empty system. So therefore, no warm-up is required. Yeah, because in the last tutorial, we went through and did some warm-up simulation of however much time to try to get the system into more of an equilibrium state. But here we're actually saying, no, like the system should start empty in this case. So we'll use 20 minutes of cooldown. We'll run 10 trials to get a measure of the average number of customers that pass through the system. To find the average number of customers that pass through the system, we can count the number of data records that have passed through the node 3, the till. Sure. So we've been given a thing to estimate, and we're going to estimate it. So we'll go completed customers, and for trial in a range from 0 to 9, q seed, and we'll put in the seed number to be the trial, and we'll have simulation q dot simulation, and we'll pass in our network. Then we'll run the simulation. So we'll go simulate until maximum time. And in this case, we're just going to put in the number, which we all assume is correctly calculated for us to include the cooldown. And then we've got our records. So after we've run the simulation, we can get all records. And then we are going to want to know what the number of completed services are specifically at node 3, because that's really the only place it counts for to say that they were completely served. That in some sense, the simulation, you can think of the whole cafe as a service where people come into and out of that system. That could have been a single node system, but this system has internal structure we want to explicitly model, and it's really where we count it is where they leave this system. So number completed And we've got this lovely list comprehension here, R for R in I used the word records there, if R dot node equals 3 and R dot arrival, I need to double check the code example. Okay, so here we're saying arrival date is less than 180. And that's because of our cooldown that we don't want to include. Oh yes, and we're going straight for the length there. Okay. And then we'll say for our list that we're building up across trials that we've got completed customers, and we're going to append the number completed. And I just want to double check that that's the end of the example. Okay, and then they're just calculating at the bottom there the average. Oops, I jumped to the top there. Yeah, okay, so let's just calculate the average then. And we're going to also print it because we're going to run it from the command line. So we got completed customers. We've got the length of our completed customer trials, which I guess you could calculate directly from here. We also know that it happens to be 10 trials because we used the range object, and we could have included that as a parameter and whatever, but that's as a constant parameter or whatever, but that's fine. Node 1 does not have attribute nodes. I see. So speaking of catching little typos, sometimes my brain forgets if we're talking about plural or singular. There we go. So we got an average of 81.9 average completions during that period of time. And that's our first example with a network that kind of feels like it's really a network as opposed to saying, well, here's a network that has a single node in it. Now we've actually got routing going on. We've got multiple nodes for which we've got customers going from one place to another within the simulation. In future tutorials, we'll look at how to control that flow so that it's not just completely random selection of, say, split percentages 30-70. We can actually have a great variety of different rules about where customers go next. And there's lots of other customizations. Almost every major component that we've looked at, there's some way to customize it using Q. Okay, so with that, thank you for watching. Hopefully you got some value out of putting together this simulation object with me, and I'll see you in the next video.